Welcome to another series of physics practicals part 4 by KET Academy. So in today's video we are going to be looking at the experiment to determine the speed of sound in trapped air, or simply the speed of sound, using a tuning fork and a tube. So normally, before you start your experiment, you need to jot down the frequency of your tuning fork, and you get the length of your tube, or you use a tube that is already calibrated, or you'll be the one to actually do the calibration. So when looking for the value, or when determining the speed of sound in trapped air, there's usually one common difficulties that many students face, which is actually calculating those harmonics and the overtones. So at the end of this video, or close to the end, I also included video tutorials on how to get these values, in order to apply in your formula to get now the standard speed of sound in air. So before we get into the video, I would advise you that whenever you're carrying out any experiment of a standard value, let's say the experiment to determine the acceleration due to gravity, g, which is usually on approximately 9.81 or 10 meters per second squared. If you're doing your experiment and you find out that your value is coming out to be 14, obviously you're very wrong, and writing that in your examination paper is going to, it means you are exposing yourself, you're going to fail yourself. So to be wise, the best thing you do is you write an approximate value, which is maybe something like 10 or 11 or 8. So that way you're going to show the examiner, the GC examiner, that your experiment was accurate, because the examiner will never take a calculator to punch your values, so you only be the one to expose yourself. So the same thing applies to measurement of speed of sound in trapped air. So what we're trying to get is, at the end, a value that is close to 330 meters per second, because we know that the speed of sound in air is 330 meters per second. So always make sure to be in the range. So now this is actually the part 4 of this video series. I uploaded a part 1 and part 2 for physics practical, which is on measurement of using your vernier caliper and a micrometer or a screw gauge to measure the diameter of instruments. And the part 3 is on the experiment to determine the resistivity. So since we don't know what the GC board is going to ask in your examination day, so the best thing to do is to watch all of these tutorials. I'm going to put a link to the part 1, 2 and 3 in the description box, and also in a card above the video. You can click directly from there. It's going to pop up. You can click directly from there and watch the part 1, 2 and 3 before you continue with the part 4. So please, if you haven't subscribed to this channel, make sure to subscribe, because I'm not going to end just at the level of uploading videos on practical sessions for the GC, but also I'll be uploading videos on the paper 1 and paper 2 solutions to past questions. So if you face problems with those parts, you can always make sure to subscribe and turn on the bell notification, so that you always be notified whenever I upload the videos. So now let's get into the video.
One speed of sound lab. The first thing I do is get a tuning fork from the teacher. There's a frequency written on it. This one is 426.7 for the musically inclined. That tells me that that is the note A. Tuning forks are never to be struck on the lab table. We can strike them on a block of wood, we can strike them on the heel of our hand, we can strike them on a shoe, but they shouldn't be struck anywhere else. We begin by taking the PVC piping, find the inside diameter of your tube. That would be from inside wall to inside wall. I don't care how thick the plastic is. Fill up the graduated cylinder with water. It doesn't need to be filled to the top, to the 1,000 milliliter mark. All we're doing is we're using the water to cap the tube. The PVC tube has centimeter markings on it. Please insert the tube in the water so that the 0 is at the top. We're going to strike the tuning fork on the wood, hold it above the tube, move the tube. You may have to strike the tuning fork again. You're listening for the point where the sound gets louder or it resonates. I've just located it. Can you hear the difference? Next, you're going to read the marking where the tape is on the side of your PVC pipe. Record that number on your lab sheet, and you're good to go.
Closed-ended air columns would be like a clarinet, as an example, where the player's mouth would be at one end, essentially trapping air from moving there, and the other end of the instrument would be open, allowing for an antinode to take place because air molecules are able to vibrate freely. So in a closed-ended air column, the math's a little bit different here. Conceptually, still the same. We're just adding nodes every time we go from a first to a third to a fifth harmonic. But we'll notice there is no second harmonic. There is no fourth harmonic, and it's not just because that's what we chose to pick. It's literally physically impossible to have a second or a fourth order harmonic. Maybe stop and pause for a second and see if you can figure out why that is. I'll go through it now, but if you do figure it out on your own, you're in really good shape. So in a first order harmonic, for a tube that is closed at one end and open at the other end, well, the closed end is not going to allow for air to vibrate back and forth, so we start on a node. The open end is going to allow for air to vibrate freely. So in a first order harmonic, we would have one node on one side, an antinode on the other. In order for that to happen, though, we can only have a quarter of a wavelength fit inside of this tube. And here's the reason why. Again, if we took a look at what a full wavelength looks like, it would look like this. Right? So basically what we have here is only 1/4 of a wavelength, because we're essentially going from this node, so that would be representative of this on a wave, up to an antinode, which would be up here. If I were to split this wave up, we'd see that that's only 1/4 of this wave, clearly not drawn to scale. So we've got this happening right there. So what that means for our formula then is that there's only 1/4 of a wavelength that is equal to the length of that tube. Or restated, we've got a length of a tube. That length fits 1/4 of a wavelength inside of it. Now there is no second order harmonic, because a second order harmonic would look like this, where we'd have a node at one end, go up to an antinode, and a node at the other end. But physically we know that's not possible. If we have an open end, air is going to be able to vibrate freely. So it doesn't make sense that we would have a node there. So we would end up going to a third order harmonic instead, because literally physically it is impossible for us to have a second or a fourth order harmonic or any other even number, because we have one open end, one open end, and one closed end. So for a third order harmonic, again, it would be just as similar to a string or a closed-ended air tubes or open-ended air columns, I guess I should say. We just continue to add nodes. So here we only had one node. So for our third order, we're going to throw a second node in there. How do we do that? Oh, we've got 1/2 of a wavelength that happens here, and then that wave continues on. Oh, that's kind of cool. I didn't even know this program could do that. So we've got our other quarter of a wave here, and it would normally continue on this way, but again, it ends up coming back the other way here, because these ends will allow each other to vibrate back and forth and will form an antinode. So we end up with how many pieces of a wave here? We've got a quarter here, another quarter here, and another quarter there finally. So our final formula becomes L equals 3/4 wavelength, because again, the knowledge is that we know there's 3/4 of a wavelength that fit within the length of this tube. Or again, restated, the length of this tube will fit 3/4 of a wavelength within it. And with a fifth order harmonic, again, fourth order harmonics are impossible on closed-ended air columns, or at least one end closed on an air column. With fifth order harmonics, again, we just continue to add more nodes. There's one node here, two here. There will be 1, 2, 3 nodes here. Trace our waveform in there, count up how many pieces of a wave we have here. 1, 2, 3, 4, 5 quarters of a wavelength there. So we'd be able to say, oh, the length of this tube is able to fit within it 5 quarters of a wavelength. And again, it may not make sense, like why would we even do something like this? But in order to figure out the frequency of different instruments in tuning them, not as in a musician tuning them, but somebody at a factory actually tuning what the shape of an instrument would be, we have to figure out how much of a wavelength can fit in here first, so that we can then figure out later on how much what the frequency of each one of those waves would be. So that is vibration modes in a nutshell, or standing waves in a nutshell. Something like a flute, which would be open at both ends. So we'll notice that the waveform appears a little bit different. Rather than starting on a node, we actually start on an antinode of a wave, and the node will happen in the middle. The reason that these antinodes are at the end is because if we think of a flute being open at both ends, we're allowing for air molecules to vibrate at those open ends, whereas a guitar string, which we just did above, is not able to vibrate back and forth at the ends because it's literally trapped to the instrument. It's stuck on the instrument, or screwed onto the instrument. So with flutes, they can vibrate at both ends. Organs, in a way, are similar to open-ended air columns as well. So what ends up happening is we'll see that there's an antinode at both ends. Well, how can we have an antinode at one end and the other end? We must have had to have crossed through a node at some point, being right here. So in order to figure out the wavelength for this diagram, we'd have to know, again, the length of the tube and how many wavelengths actually fit inside of it. Well, if we think of a full wave would look like this. We could break that up into multiple pieces. So right here is only a quarter of a wavelength. How we know that it's a quarter of a wavelength is because if we were to look at this diagram, we could say, well, this is a full wavelength. This would be a half wavelength. This would be a quarter wavelength, or a wave split up into quarters. So basically what we have going on here is we start on a node. We're basically starting here, and we're going through a node. Sorry, I think I said it started on a node. We're starting on an antinode, my mistake, and then we're going through a node, and we're coming back down to another antinode there. So what we have drawn here, the red portion, or the red wave, is identical to what we have drawn up here. So there's a total of 1/2 wavelength in here, because we have a quarter wavelength here, right? 1/4 of a wavelength, and we have another quarter of a wavelength there. And of course, a quarter plus a quarter equals a half. I'll get my chicken scratch drawing out of the way here so it's not distracting the rest of the way here. So in order to figure out the length of this wavelength, we could say, well, the length is equal to 2 quarters. Length is equal to 2 quarters of a wavelength. Or we could say it's equal to 1/2 of a wavelength, which probably makes a little more sense than saying 2 quarters. I personally like to actually leave it as 2 quarters because I feel like the concept matches the math a lot better that way, since there are literally 2 quarters of a wave here. For a second order harmonic, it operates very much, open-ended air columns operate very much similar to closed-ended air columns in the fact that we're just adding nodes every single time we're going from 1 to 2 to 3 to 4 to however many harmonics we're dealing with. We just continue to add nodes. There is 1 node here, now there's 2 nodes here. How can we have 2 nodes? Well, we must have started on an antinode, because again, open-ended air columns always start and end on antinodes. We must have had to pass through a node, had another antinode in the middle before we could get to another node again. So if we count up how many wavelengths there are here, there's a quarter right there, plus another quarter, another quarter, another quarter, which gives us a total of 4 quarters of a wavelength, which of course would be the same as saying 1 wavelength, or just the length of this tube is equal to 1 full wavelength. Now, in a third order harmonic for open-ended air columns such as a flute, we just again continue to add more nodes. There was 1 node here, 2 here, now there's 1, 2, 3 nodes there. And the reasoning is very similar to the first and second order harmonics, where how do we get from an antinode to another antinode with 3 nodes in between? Well, we've got to have more quarters of a wave thrown into the diagram. So if we take a look at this, we have 1, 2, 3, 4, 5, 6 quarters of a wavelength. So the length of this tube is able to fit 6 quarters of a wavelength within it. Better way of saying that would be 3 quarters of a wavelength. Halves of a wavelength. All right, so let's take a look at closed-ended air columns then. Go look at vibration modes and standing waves. So basically what a standing wave is it's a wave that gets trapped, or at least pieces of waves that get trapped within a confined space. So as an example, we could think of this first example here, this first harmonic, and we'll define what a harmonic is in just a moment. This first harmonic, we could look at this as a guitar string. A guitar string is attached at both ends of an instrument, one on the neck of the guitar, one at the body of the guitar. And when plucked, it vibrates at a frequency. It vibrates at its first natural frequency, which is what the first harmonic is. And what happens when that guitar string is played is a wave will travel from one end down to the other end of the string. And now normally a wave would continue to move on. Right? We've got a crest, we've got a trough, which makes it this a full wave, but instead this wave can't go past where the guitar string is attached to the body, so it turns around and travels back towards where the sound came from, or where the vibrations came from. And this will happen over and over again, and the wave will interfere with itself. The incident portion will interfere with the reflected portion, and it will give us this standing wave pattern. Standing wave pattern because it appears to stand still. All right, so now I'd like to take a look at how we can actually put a formula to this. So let's say we knew the length of this guitar string. We could measure it. Length could be denoted by an L, and we could see how many wavelengths are trapped within this boundary. So if I wanted to figure out the overall wavelength, I could say, well, L will represent the length of the string. We've got the knowledge that this is only half of a wavelength that fits on that string. So we could say, well, the length equals 1/2 of a full wavelength. So that's where I'm getting this formula from. There's literally 1/2 of a wavelength that is equal to the length of this string. And then from there, I could figure out all sorts of cool stuff. I could figure out what the frequency is of this wave. And if I plugged it back into our V equals lambda F equation, right? Now I know the wavelength. I know the speed of sound that travels across this string. We could look it up. We could be given it. Within open air, speed of sound is around 340-ish meters per second. That does change with environment. But then I could know my velocity, and then I could figure out what frequency this actually vibrates at, which would then correspond to an actual musical note. We don't have to get there quite yet. I just want to at least show you that there are additional things that we could go from here. So in order to figure out a second harmonic, we would be able to say, well, how many wavelengths are there within this length? Throwing that into a mathematical formula, we could say, well, from here to here is a length of string that the wave is traveling down. How many waves fit across that length of string? Well, there's one half here, a second half here, so this would be one half and the second half of a full wave. So there's one full wavelength that fits on this string. So whatever the length of the string is also the length of the wave. And how we get a second harmonic is by essentially cramming more wavelengths into the same amount of space. Or we could think of it as allowing for the string to vibrate at double the rate that it did in a first order harmonic. We'll notice something about this formula. There's a couple of different ways we could write it. This is a more conceptual way, right? Because the length is literally equal to 2 of those halves. So if this was, again, the length of the string, there'd be 2 halves there. But of course, mathematically, it doesn't really make sense to say 2 halves. We absolutely could, but it's easier to just say, well, 2 halves, that's 1. Or we could go even easier and say, rather than length equals 1 times the wavelength, well, 1 times anything is itself, even if it's a variable. So the length of the string is equal to the wavelength of this wave. All right, to get a third order harmonic, same deal. We just continue to move on. We'll notice that there's no node, or I guess I shouldn't say no nodes. There's 2 nodes here. There is 1 node in the center here, a total of 3 nodes. And there's 1, 2, 3, 4 nodes here. 2 of them are in the center. So we just continue to add more and more nodes as we get more and more harmonics. So we could go with a 4th, a 5th, a 6th harmonic. We can go on ad infinitum. But we are only going to go up through the 3rd order harmonic. All right, so in order to figure out the wavelength of a vibration that is occurring in a 3rd order harmonic, we'd be able to say, well, there's 1 half of a wavelength there, another half here, and then yet another half over here. So the length of this string allows for 1, 2, 3 half wavelengths to fit on it. Or L equals 3 over 2, 3 halves. And we could write this as a decimal as well, but usually I just leave it as a fraction. There's not one way that's more right than another way necessarily, though. All right, so that is wavelengths and vibrations on a guitar string or in closed-ended tubes. So in open-ended tubes, or open-ended air columns, this is more representative of